Well, so good morning and welcome back to this lecture on polynomial interpolation. Yeah, so there are various kinds of interpolation we will be going through in this topic. So we'll start with what is polynomial interpolation and then about its existence and uniqueness part in the first maybe half an hour or a little more than that. And then how much error do we have in interpolating polynomial? That will be also covered in this first part itself. So what is interpolation? So interpolation is a process of estimating values between the given data or non-data points or approximating complicated functions by simple polynomials, right, or determining a polynomial that fits a given set of points. So in each case, whatever I have mentioned here, three different scenario, but the point is that some given data points are given, whether a function is complicated function is given. In that case also we can compute, some these data points, and then the idea is that the polynomial which passes through the given points. Yeah, the polynomial which passes through the given point, that is the idea of the interpolating polynomial. Yeah, so I think it's clear. So here I have mentioned like that known data points, the values between. So once these values were given, then we have fitted a polynomial. Then we can approximate that what is the value here, what is the value at this point here, what is the value here. So all these between points, intermediate points, we can find out the values or approximating complicated functions. So some very complicated function is there where, for instance, just an example, that it is difficult to get the integral of that function. So what you will do, you can approximate that function first by polynomial, and then you know how to integrate polynomial or in fact differentiate a polynomial. So that's the idea of the motivation behind this interpolation, the polynomial interpolation. The other one is that again similar, that some data points are given and you want to fit a curve, again for the same reason which I have mentioned before, that in that case now you will be able to find all these unknown data points. So here the value is not known, then you can approximate by this fitted curve. So that is the idea of interpolating polynomial. Well, the applications, as I mentioned already, that constructing the function when it is not given explicitly, only the values of function are given at some points. Yeah, that is the first. Of course, you want to construct a polynomial which passes through the given point, and then you can have various applications of that function. You can integrate that, you can have these missing values, unknown values, and so on, so many applications. Replacing complicated function by an interpolating simpler function, because see, usually polynomials are very simple functions, so therefore we are talking about here the polynomial interpolation. But in general, interpolation is a rather general term where not necessarily the polynomials have to be fitted, but you can have some other simple functions which can be fitted to the given data point. But we'll be talking about polynomials only. So that many operations such as determination of roots, differentiation, integration, or many other operations may be performed, because all these operations are easier to perform on polynomials. So that is the idea of considering these simple functions, that is, it means the polynomials. Well, so what is the fundamental principle behind this polynomial interpolation? How do we expect, or where this discussion started, that we can approximate by polynomials? Yeah, so the idea has come from this Weierstrass approximation theorem, which says, and you know that, suppose f is function defined and continuous on interval a b. Then it says that for each epsilon, whatever small epsilon you choose, there exists a polynomial px with the property that the difference between that function and the polynomial you can always, set to less than epsilon. That means you can approximate the function, the given function, by a polynomial as good as you want. As good as means the epsilon you are choosing, right? So if epsilon is very, very close to 0, that means this function f and px, they are very close to each other. So this is the idea that why the polynomials were chosen, because we know that whatever function is, whether it's a very, very complicated function, sorry, there is a problem here. So whatever complicated function we have here, yes, then we can always approximate by the polynomial. So this function was complicated, where we could not perform many operations, like I mentioned some of them: determination of root, differentiation, integration, and so on. We are not able to do for certain complicated functions. But once you approximate, and the approximation, you can go as good as you want. So once you approximate by the polynomial here, and then you can do all those operations on the polynomial. So but the idea is that how to approximate and all, how good is the approximation, all those questions are open, that we will discuss briefly in this lecture itself. So the another question is that why not Taylor's polynomial? You see, Taylor's is also a polynomial. We have studied there, that can also be used to approximate a given function. So why we are talking about something else now, which is we are calling as interpolating polynomial, this polynomial interpolation. So what is basically the difference on why this interpolation polynomial is different from having a Taylor's polynomial as an approximation? So consider this example I have given in your mathematics 1 also. So consider this Taylor polynomial of e power x around x is equal to 0. So if you take the Taylor's polynomial of 0 degree, then you have only 1. That means, so this is the original function e power x, and then you have here this polynomial of 0 degree, so 1, 1, the constant 1. Once we go with having more term, that means p1x, the first order polynomial, 1 plus x, that means now the approximation is going to be by this polynomial. Now let's increase that. So just plot this p3 here. So if I plot this p3, well, this is approximating now better. The more the degree is, the better fit we will expect here. So for instance, if we go up to p5, this approximation is very, very good to e power x, and you go for 10 order or 15 order, then you will hardly see that difference between this e power x and that polynomial. So we have that property of the polynomial, which is again the same, that you can approximate the given function by a polynomial, right? Good. So the point here is that the Taylor's polynomial agree as closely as possible, that is true, with the given function at a specific point. So they concentrate their accuracy near that point. One thing is which you should have mentioned here, we have taken in this expansion, the Taylor series expansion, around this 0. So in fact, if you go with lower degree polynomial also p1x, that is absolutely matching, of course, at 0, and in the vicinity of 0 also we have a good match with e power x. Then we increase the degree, and you will realize that again, of course, it matches at 0, all will match at 0. And then this interval where it is very well matching with the e power x is increasing. So as you go further, then you have this interval of good approximation is further, more. So the point here is that in Taylor's approximation, your polynomial passes through only this one point, and then in the vicinity of this you have the accuracy of the approximation. As you go far, then your polynomial is not very accurate. So the accuracy here concentrate near that point where you have considered this expansion. But for ordinary computation purposes or for many applications, it is more efficient to use methods that include information at various points. So in the Taylor's polynomial, you are using all information of that function at one point. You need the function value, you need its first derivative, second derivative, third derivative, fourth derivative, and so on. The more you know, the better fit you can get with the polynomial. But in this interpolation or the polynomial interpolation, the idea is different. We don't need all these information, the first derivative, the second derivative, and so on. We need only the function value at different points. So the two are completely different. The Taylor polynomial is different. The concept is different. The derivation is absolutely lie on having this information at one point of various derivatives. But in case of polynomial interpolation, you need values at different points, value of that function at different points. So it is very different. Now we come to existence and uniqueness of polynomial interpolation. So this is the important result which I will explain here. So for n plus 1 data point, yeah, n plus 1 data point, there is one and only one polynomial of order less than equal to n that passes through all the points. The simple to remember this, for instance, you have 2 points. What will be the unique polynomial which passes through these points? That will be the straight line. So if 2 points are given, then you have a polynomial of order 1. If 2 points are given. Why less than or equal to 1? Because this may happen that there are 3 points, but still you have only the unique polynomial, which is the straight line, right? So 3 data points were given, and then 3 data points were given, and we have our degree 1 polynomial. Correct? So that is the result here, that n plus 1 data points, there is one and only one. You cannot have 2 straight line passing to this point. It is going to be only one. But if you lose the restriction on the degree here of the polynomial or the order of the polynomial, then anything can happen. So you have these 2 points. This is a quadratic polynomial, then this can be also a quadratic polynomial. That uniqueness thing is gone if you go beyond that order n for given n plus 1 data point. So the uniqueness is coming when you have a polynomial of order less than equal to 1. So for n plus 1 data points, there is one and only one polynomial of order n plus 1 that passes through all the points. I think that is clear and we should have this in mind. For example, there is only one straight line that passes through 2 points we have discussed. Consider for simplicity why unique and so on, that will be clear also from this derivation. So a second order polynomial. So we have a0, a1x, a2x square. That's a second order polynomial, second degree polynomial. And how to, now the question is that 3 data points are given, suppose, right? 3 data points are given, x0, y0, 1 data point, then we have x1, then we have y1, another point, and we have x2 and y2. These 3 data points are given, and you will see that this is going to be a unique polynomial of degree 2. It will the polynomial which passes through all these 3 points will be a unique polynomial of degree 2. So a straightforward method for computing the coefficient. So in this polynomial, what are unknown? Unknowns are these coefficients. These are unknowns. So we have the 3 points, yeah. So for n degree, we will take n plus 1 data points. So here we have second degree polynomial. We need 3 data points. And then we can compute all these unknowns. So what are these? So suppose we have three data points x0, fx0, x1, fx1, x2 and fx2. These are the three data points given and we want to fit this second degree polynomial. So we know that this polynomial must pass through these points here. So we have x0 point, x1 point and maybe here x2 point. Correspondingly, we have these values given and we want to know what is that polynomial which passes through all these points. So if this polynomial is passing through, that point, it should satisfy that. So we will just force this to satisfy. So we have fx0 is equal to a0, a1 x0, a2 x0 square. Similarly, fx1 and then fx2. So this polynomial is satisfying all these 3 points. So you have basically 3 equations, right? You have 3 equations in a0, a1, a2. But that just having 3 equations, 3 unknown will not guarantee you that you have a unique solution, will it?
No, sir.
Yeah, so that will not. So we have this ax is equal to b, the system of equations. Ax is equal to b, that is the system of equation. If it has a unique solution, then that's fine. We are done with that. There will be a unique second degree polynomial which passes through these points. These equations has a unique solution because if you compute this determinant, just compute that determinant. You compute that determinant x0 and then this will come as x0 minus x1, x1 minus x2 and x2 minus x1. What do we see from this now? If the determinant is this one, x0 minus x1, x1 minus x2, x2 minus x1. See, x0, x1, x2, they are distinct points, correct? They are 3 different points we are talking about, right? x0, x1, x2 are 3 different points. So if these are 3 different, this is a non-zero, this is non-zero, this is also non-zero. So overall we have a non-zero determinant. And what does that mean?
3 independent values.
So unique solution, right?
Yes, sir.
Yes. This,
Yes,
if
sir.
these are distinct, which is the case because we are talking about the 3 data point we have taken x0, x1, x2. So if we have the 3 data points, then this system will have a unique solution. And the only point here is this is fine. Yeah, so this is exactly the interpolation we are talking about, that if 3 points are given, you fit a quadratic polynomial. If 10 points are given, you fit a polynomial of degree 9. And how you will get such a system of linear equations? You can solve this system of linear equations and then we can substitute those unknowns there, a0, a1, a2 and so on, and then you have the polynomial. So how to get the polynomial, is that clear? If 5 data points are given, what you will do?
So create like assume a polynomial of degree 4.
Degree 4. So like a0, a1x, a2x and a3. Sorry, ax and a3 x square, a0, a1, a2, a3 and a4 x cube. Oh, 3 here, then 4 here, right? So we will create this one, our polynomial p4x, and then we will get those 5 equations in these 5 unknowns a1, a2, a3, a4, and then we will have a similar kind of this ax is equal to b, which we can solve, and we got the polynomial. So it's not difficult getting this polynomial because it's actually left to the solving system of linear equations. The question is why then we are learning this as a different topic. This is done in principle, this is done in 20 minutes, but we have to, we cannot finish probably in 2 hours today. The point is now in practice it is observed that the above system of equations is ill-conditioned. I have mentioned a little bit there in the system of equation, and naturally here also we will not go into detail, and there also we have not discussed that into the detail. But you have that notion that some system of equations are ill-conditioned means, if I remember, I mentioned there that even that truncation error, because every computer or your calculator, they are truncating the number. Even that truncation error will lead to something very different solution, not to the actual solution. Even you have a Gauss elimination or you have any other this iterative methods, they are very sensitive to the parameters. Wherever you have such a system, a1 x naught square, then x naught cube, x naught 4 square cube of that number. So it is observed that once we have this whatever the system of equations we are getting out of these polynomial interpolation, when the degree is large, of course, for 2 and 3 it's not a problem. For example, you have a 9-degree polynomial or so, then solving the system of equations is not easy. You cannot just solve by Gauss elimination or those iterative methods because of the highly sensitive system, and these are called very ill conditioned. So solving those systems, you really require special attention. Even special methods are there which somehow control that portion, and then you are likely to get some good approximation. But again, even I have experienced those systems in my research. You cannot solve them actually. So very little error will lead to something very different at the end, which has nothing to do with the solution. So they blow up sometimes, and they can diverge to some other values and so on. So many things happen in the ill-conditioned system. So the point is here is for you, because we are not going into that detail about how ill-conditioned and checking those condition number and so on. We will not go in this way, though it's fine. That the idea is clear. You need to just solve the system of equation and you are done. Because once you have a large system, you need some numerical approximation, and those getting numerical approximation is very difficult for these systems. So whether they are solved with an elimination method or more efficient algorithm, the resulting coefficient can be highly inaccurate, in particular for large n. This is what I also mentioned here. Therefore, what is the remedy? Therefore, we have some mathematical formats which we call interpolating formats, in which such calculations can be avoided. So the discussion of this chapter is that without solving such a system of equations, how to get that polynomial, how to get that quadratic polynomial which we are talking about here without solving this system of equations. Such system of equations. That is the idea now of this chapter. So since that interpolating polynomial is unique, yeah, your three data points are given, then you will have a unique quadratic polynomial or maybe a linear polynomial. But that is going to be unique, which passes through those 3 points. Either it is quadratic or maybe some coefficient, the higher order coefficient is 0, then it is just the linear one. But whatever, it's linear or quadratic, but it is going to be unique, which passes through those 3 points. So before we discuss that how to get without solving this resulting system of equation, we first consider that how much error do we have in that interpolating polynomial, because this is unique. Whatever format we are going to discuss there, that you do in this way, do in that way, do and so on, that polynomial is going to be same. That will not change. So we can discuss before we move to those formats, different interpolating formats, how much error do we have in that case, because there is certainly an error. You are just approximating a given function. So as we discussed there, that our function is, for instance, this one in a and b, and we want to approximate by the polynomial. So you can generate few data points here out of that, and then you can approximate that with the polynomial which passes through these points. Yeah. So there is error. Definitely there is an error between the two, because you cannot expect having this finite degree polynomial, and you cannot expect that it will match exactly, because for that you have to really for the accuracy you have to go for really high degree of polynomial. So if you have low degree polynomial, there will be more error. If you have a very high degree polynomial, the error will be minimum, so will be less. And here we are talking about that, what is that error, how much error do we have depending on that number of points we have taken or the degree of polynomial we have for the approximation. So suppose we have x0, x1, xn, n plus 1 data points, and x be a point belonging to the domain of the given function, right? Is that clear statement? So we have here these x0, x1, x2, x and xn points, and then we have x, which is somewhere between, right? Not exactly those points where the value is already known. So that is your x, and then you want to see basically that how much a difference you have from your polynomial. This is, for example, polynomial passing through that. So there is some difference between the function and the polynomial. How much is that? We will be talking about here. We assume, of course, that the given function which we are approximating by the n degree polynomial, that is n plus 1 at differentiable, that n plus 1 times differentiable, where ix is the smallest interval that contain all these data points, and also your x, because you are now computing that error at that x point, which is not the data point. Data point, of course, it
So
is
can you please
passing through.
explain again what is the meaning of CAN plus 1 x? I didn't get that.
This is that the function is differentiable up to n plus 1 th derivative. That this f
Okay,
n plus 1 th you can compute, right?
okay, so got it.
If you just say f belongs to the C, that means the function is continuous. If we say f belongs to C1, that means the function is differentiable one time. If you have f belongs to C2, the function is differentiable 2 times. Fine. Okay.
Yes, sir.
So here we have these points where the function, where the data points are given, and then we have this function, and there is a point x where we will discuss the error between the two. Then the interpolation error at the given point x, any point x in that interval you can take, is this one, that fx minus pnx, fx minus pnx, the function value, the exact value, the polynomial at x, polynomial value at x, and this is given by this one, the n plus 1 derivative at the xi point. Xi is also somewhere there in this interval, factorial n plus 1, and then you have x minus x0, x minus x1, x minus xn. So this polynomial passes through exactly those points. So the error at those points x0, x1, xn is going to be 0. That is obvious from here also, or from the derivation itself, that this polynomial, your p n x polynomial, will passes through the function, right? So fx0, the p n x1 is going to be fx1. The p n x2 will be fx2. This is obviously true, because your polynomial will pass through all these points, fx0, fx1, and so on. So here also, if you see the error, for example, if I replace here x by x1, then because of this x1, this is going to be 0. But other than those points, x0, xn points, when you have any other point, you can estimate, or the error will be given by this. Why to estimate? Because this actually xi is not just known. So you can, at most what you can do with this formula, this is going to be useful to have this approximation of this error, that how much error we have at most in our computation, so that you can estimate this derivative. You can estimate, rest is known. So that is the only the benefit of such a formula. I have the derivation.
Excuse me, sir.
Yeah.
Sir, this is for only for approximating functions, that it should be n plus 1 times differentiable. For the data points interpolation, we don't need this error.
Yes, because see, when the data point, only the data point is given, we don't know the actual scenario, right? If I say the only the data points are given, that these are the data points, and you fit a polynomial, and then you have fitted a polynomial. So I don't know exactly that what was the original function, so I cannot talk about the error. That is true, isn't it?
Yes, sir.
Yeah, because I don't know. I have only the data points. I can fit it. That's all. Nothing else I can do. But this is to consider that in reality, what is happening if I have, for example, that function which was the original function which passing through this point, then I can understand from here that how much error actually I am making when I approximate by the polynomial. Yeah, this is the idea here. So your question is true, clear, that if only data points are given, we are not aware with what function is the actual function which will pass through this, we are not familiar with. So naturally we don't have the idea of the error or that function itself here. So that does not make sense here. Fine. So here,
Excuse me, sir.
yeah.
Sir, this error term is quite resembling to that Taylor polynomial reminder term, right?
Yes, true.
Like,
So
is it the same or like, I mean,
it is
what?
not same because you have a this term here which you don't see in your Taylor expansion, that is a different term slightly. Because there
Okay.
you have only one point now where you are expanding that, but you have
So
rightly
also there
Like,
there in
yeah, there
the,
are many points.
like the interval is 0 to 1 of psi, this one. 0 to x, sorry. 0 to y.
yeah. So there is difference, but you have rightly pointed out this is actually coming from the Lagrange the Lagrange mean value theorem. Yeah, we have studied Lagrange mean value theorem. So that application is there for the derivation of this, and that is exactly the Taylor. Yeah, Taylor's is more general than the Lagrange one. So it is the just coming from the Lagrange interpolation, the Lagrange mean value theorem we use in the derivation. So derivation is there in the slides, but I am not going to go through all the derivation now in the lecture. So if you are interested, you please go through. I am sure that it is neat and clean. You can understand. If you again have any question, you can get back to me. But there are 3 slides which I am skipping here now. But so we need to just keep in mind that if at all the error is concerned between the actual function and the polynomial which we have derived here, then that error is equal to this one. We will have one example at least where we will see how to utilize this one.
Excuse me, sir.
Yes.
So can we say here from the error term, I mean, it looks as if that the error term is a polynomial term, polynomial of n degrees where the roots are x0, x1 up to xn.
Yeah.
So, from
Yeah.
the
Why the root? Because this E and X satisfies
yes, it
exactly
becomes zero at those points.
yeah, at 0 at those n+1 points.
Yes, sir.
Yeah. So exactly those considerations and all are there in the derivation. So absolutely. So based on those Lagrange mean value theorem, the roots of this and so on, we have derived the formula. If today itself, if the time permits towards the end, if we are done with the whole lecture, then we can think of going quickly through the derivation part. Yeah. Otherwise, I will put in the slides. Some of you who are interested can go through the derivation also. Is it okay? So we move to the next one. So we are not going to derive this formula in this lecture now. So what we are going to do now? We will read the forward and the backward difference table now in this lecture. Also the Newton's forward interpolation formula, Newton's backward interpolation. So these are the two which we will learn next. One is the Newton's forward interpolation formula. One is Newton's backward interpolation formula. So these are exactly those formats I was talking about for those polynomials without computation of that system of linear equations without solving those system of linear equations, how to write down the polynomial which passes through those n+1 data point, how to write that nth degree polynomial. So these are the two formats we will be talking about first, and then there will be two more which will follow in this lecture. So to have these, to write down these interpolating polynomials, we need something so-called forward and backward difference table. Because with the help of the table, the given data point, with the help of the table, it is very easy to write down those polynomials, as you will see there. Though in the theoretical portion, you may not like it very much, but once we do the numerical computation, this is going to be very straightforward, that how to write those polynomials. So what we have learned in this lecture is in the previous lecture, what is the interpolating polynomial that we have seen, and existence and uniqueness part. Also, we have seen that there is only one and only one polynomial of order degree less than equal to n, which passes through n+1 data points. And you have to also remember that the error in interpolating polynomial is given by such an expression. So with this, we will now move to this different methods of interpolating polynomial, and these are the Newton's forward and the backward. So although there is a unique nth order polynomial that fits n+1 data point, there are a variety of mathematical formats which I have mentioned in which this polynomial can be expressed. And the two we are going to discuss is the Newton's forward and the backward. After this, we will go to the next two here, where we have the Newton's divided difference formula and the Lagrange interpolation formula. Indeed, this Newton divided difference formula is not as such there in the syllabus, but since this is very much related to what we are learning here, so I will just mention, because this is more general. The Newton's divided difference formula is more general. In what sense it is general, I will mention at that point itself. And then at the end, the Lagrange interpolation formula. So basically three are in your syllabus: the Newton's forward, Newton's backward, and the Lagrange interpolation formula. These three. So Newton's backward and forward interpolation formula. So we are preparing for that. So some notations are required, some operators are required here, which are very simple. Just believe me. So let this tabular point x0, x1, xn be equally spaced. That's the first condition we are making, that these points are equally spaced. That means xi is given by x0 plus ih. So h is fixed. So you have here x0, then you have x1, then you have x2, then you have x3, then you have x4, and this difference is same. So equally spaced data points we are considering. And just let me point out here itself that this Newton forward and backward interpolation formula, they use that equally spaced data point, whereas in these two, we will use anything general. So you don't need to take equally spaced data point. Whatever data points are given, in whatever differences are there in between, you can apply always this Lagrange, or you can apply this Newton's divided difference formula. But for the Newton's forward and backward equally spaced points, which are given here. So one is the so-called shift operator. E. What is shift operator? When you apply this E on fxi, it will give you the value fxi plus what? Xi plus h. Xi plus h. In general, this is going to be like En and fxi. If you apply like E2, let's say E2 on fxi, that will be just fxi plus 2h, right? So whatever this here, it will go here. That's all. In fact, with the notation will go like if you have e power minus 1 xi, that is simple xi minus h. So these are the shift operator. Yeah, so this is the notation that if I apply e on fxi, I will get fxi plus h. It will shift to the right. If I have e power minus 1, if I write there, that means it will shift to the left. if I have e power 2, that means it will shift 2 data points. So e fxi, e2 fxi will be fxi plus 2h, and so on. That is the shift operator we call. The forward difference operator, difference, yeah, so there should be some minus sign. So difference operator, forward difference operator is given by this delta fxi. So what is delta? When you apply on fxi, you go forward and then minus that point itself, fxi plus h minus fx. It's what this is called, forward difference operator. You go first forward, then minus, you go to that point itself, that is your delta. There is a backward difference operator. Yeah, the backward difference operator. Then you have here fxi minus fxi minus 1 minus h. Here you are going backward. Fxi minus fxi minus h. This is the backward difference operator. There is also central difference operator, which we hardly need, I think, in this lecture. But just let me mention the delta fxi is a central difference. You go half to the right minus half to the left. So fxi plus h by 2 minus fx minus h by 2. This is your central difference operator. So only mainly we need these forward, backward, and maybe shift operator. That's all. So shift means it will shift the function value, and forward difference means it will go forward and then get the difference. Backward, the difference again with the function value and the backward value. These are the notations which we will use, and they will be, used for the simplicity, because instead of writing this one, we will write just delta fxi. Further simplification we will be doing that fxi we will be denoting just by fi, another notation. Fxi plus h we will be just denoting by fi plus 1. Fxi plus h by 2 we can denote by fi plus half. So that's another notation we are going to use, and can easily be verified, as you will see that delta fi is equal to this nebula fi plus 1. Why these two are equal? Because what is delta fi? You remember it was fi plus 1 minus fi, correct? And this one fi plus 1 is equal to fi plus 1 minus fi. So they are same. Whether you say this forward fi or backward fi plus 1, they are going to be the same. Or here the delta, the difference one, that means you will go half forward. That means you have fi plus 1 minus fi. So this is also same as this one or this one. So this is some kind of relation we have that. Oh, sorry. Also, you note that this forward operator is equal to e minus 1. Why this e minus 1? They are equivalent. If you apply this forward on fi, what is the result? Fi plus 1 minus fi, correct? And when you apply e minus 1 on fi, you have again e on fi, that is fi plus 1, shift operator minus fi. So this is the same thing. The right hand side is same for both. So this forward operator or e minus 1, they are the same. Are you getting me here? Is that
Yes,
clear?
sir.
Yes, sir. Yes, sir.
Okay,
Yes,
very
sir.
good.
Yes, sir.
Simple thing. Once you go through, again, I'm sure there will be no problem. So in this backward also we have the relation that 1 minus e minus 1. The reason is also given here in the bracket, and in the delta case also we have this relations. So this is fine, and we don't need too much really all these. So don't worry about this. We will be constructing the table which will evaluate these values of these difference operators, and there you don't need absolutely anything. Well, but in the derivation, at least we need to have this idea here. So the higher order, again, we can go for the higher order differences also, that delta 2 fxi, that means you are applying 2 times this delta. So if you apply the first time here, you have fi plus 1 minus fi, and then you apply again. So then you will get fi plus 2 minus fi and so on. Finally, you will get this one. fi plus 1, fi plus 2 minus 2 fi plus 1, and then you have here fi. So this is the second order uh, differences. Similarly, the backward also you can compute, and you will get this fi minus. Someone has to be unmuted. Please unmute. Yeah, good. Okay. So what we have here, we have the higher order differences. Is that clear? Also, the higher order, we can. How do we get this? Yes, you apply 2 times. That's all. Now, the point here, the forward difference table. How to make that difference table without remembering all those formulas we have just discussed for higher order also, or the lower order, whatever. So this is going to be kind of table we need to prepare, the so-called forward difference table. So here you will keep all these data points for x. So x0, x1, x2, x3. For instance, you have these 4 data points, the corresponding values f0, f1, f2, f3. So these 4 points are given: x0, f0, x1, f1, x2, f2, and x3, f3. These 4 data points are given. These are the first difference operator. How to get those first order differences? Nothing. You subtract from this to this, this to this, this to this, and put it there. Yeah, these are the first order differences. Now you remember delta fi is fi plus 1 minus fi. So what you do here, f1 minus f0 is your delta f0. f2 minus f0 is your delta f1. f2 minus f3 is delta f2. Clear? So this is nothing but f1 minus f0. This is nothing but f2 minus f0, f1. This is nothing but f3 minus f2. So once you have these values, these points, you subtract this one from this one, this one from this one, and this one from this one. You get the next values. Now coming to the next, the higher order. Higher order was delta 2 fi, that means delta fi plus 1 minus delta fi. Same thing we will be doing. You difference. So again you go to the next step doing the same thing. That delta f1, this is delta f1 minus delta f2. The same nature of the differences. Here again subtract this from this one. Delta f2 minus delta f1. So your table is ready for the higher order differences. Then you go for the third order differences. Again, subtract this delta 2f0 from delta 2f1. That is delta 2f1 minus delta 2f0. So see, this table, preparing this table is very easy. You don't need, in fact, to remember all this formula. What you do, you keep these values there, and just differences will come here. Again, further differences will go here, and further differences will go there. And this table is ready. Well, the backward difference table is also same. So here we'll be doing the same thing. There is no change. Again, f1 minus f0, f1 minus f0. But what is in terms of this delta, or the backward delta, f1 minus f0? What do we call that? Yeah, so f1 minus f0. What is that in terms of the delta f?
minus delta
Minus.
0.
Why not
Snap
delta f1? Backward delta f1?
Yes, sir.
Yes,
Yeah.
sir.
Yes, sir.
So instead of forward f0, that same difference will be called now delta f, backward delta f1, backward delta f2, backward delta f3. The same values. True? The values are
Yes, sir.
same.
Yes, sir.
And again you difference, go for the difference. Here, what you will get, delta 2 f2, delta 3 f3. And go again, you will get delta 3 f3. So you need to prepare that table irrespective of backward, forward. We will see what to be used there in that context. But the table is same. The values are given, you keep the differences, you keep again the differences, you keep again the differences, you are done with the table. So how to prepare whether forward or backward table, it is clear.
Yes, sir.
In all those interpolating polynomial, what do we need? So I will just emphasize here itself. Once your table is ready, if you will be using Newton's forward difference formula, in that case, these values are required actually. What are these values? F naught, delta F naught, delta 2 F naught, delta 3 F naught. These values are required. When you use the backward one, these values will be used. So these in the forward, these values are important. In the backward, so table is same, right? You have prepared the table. I'm just telling you, if you will be using Newton's forward difference formula, only these values are required. These values are required. If we use the backward difference formula, these values will be required. The bottom one, the top one. Fine. Because see here, F naught, delta 2 F naught, delta 3 F naught. With respect to F naught, all these differences are known. In the backward, F3, delta F3, delta 2 F3, delta 3 F3. All these backward differences are known for F3. So for the Newton's backward formula, these values are required. In the forward difference formula, these values will be required. We will see in the derivation itself that why. But how to prepare the table, this is clear, right? You don't need to remember much all these formulas and all. So for instance, just a numerical example to prepare the difference table, right? Just to prepare the difference table. You have 0, 1, 2 x values, then fx values, you have 1, 2 and 1. So the first order difference is whether forward or backward, right? We have seen that same thing. 2 minus 1 is 1. 1 minus 2 is minus 1. Further, minus 1 is minus 2. So we have prepared the table. Given data, it will take just few seconds to prepare the table. Well, so this is forward delta F0. This is forward a second order difference of F0. This is backward F2. And this is again minus 2 is also backward second order difference F2. Yeah. So as I said in this, when we'll be talking about the Newton's forward difference formula, these three values will be used. When we will be using backward difference formula, these three values will be used mainly there in that format, in that formula. Let's go to that Newton's forward difference formula because we have already prepared the table. Everything is known now. First is the linear interpolation. We'll start with the linear interpolation. That if two data points are given, then what will be that line, the equation of that line in this particular format? You know how to fit that line. I don't have to tell you. The two data points are given. All of you can give me that line passing through those 2 points. But here in a special format, we are preparing that line only. So for instance, x0 is given at fx0, fx1 at x1, the value is given fx1. So this is the scenario. Only these two data points are given. This x0, fx0, and there is another data point is given x1 and fx1, and we want to pass that line p1x. We want to pass to these 2 points that line. That might be the actual function. We are not much bothered, but we know only these two data points. Yeah, we need 2 data points that we want to approximate by the polynomial, and that will be a unique polynomial of degree 1, only one polynomial. So consider the general equation of the straight line p1x, the polynomial of degree b0 plus b1 x minus x0. Now you will be asking that why you have taken this. Usually you take b0 plus b1x, right? Something like that. It is same only. There is no difference. You have like b0 minus, there is another term b1x0, which is a constant term, and plus b1x. Our format is given in this way, and this is some constant. So we have exactly constant plus another constant time x, but we have written in this way because of some reason. We can easily compute b0 and b1. Why? So this is a linear polynomial, isn't it? So don't get confused. This is a linear polynomial. There are two unknowns, b0 and b1. Only that format we have written in this way of the straight line. Why? That reason is clear from here, that at the point x is equal to x0, this should pass from the x is equal to x0 point. So when x is x0, this will be 0. You will get b0 directly. So what is your b0? b0 is fx0. The computation is very easy. Second, at the point x1, now you substitute there. So fx1 is equal to b0 b1 x minus x1 minus x0, and this b0 is known already, fx0. So you get b1 also ready. So what is your equation? So we have here b0 as fx0, b1 is this one here. So we know the equation. Our equation will be wait a minute. Yeah, the equation was b0 b1 x minus x0. And we are considering equidistant data point. If we consider equidistant data point for deriving this Newton's forward difference formula, this b1, your coefficient b1, so is nothing but bf x0 plus h minus fx0 divided by h, right? This we are denoting now. This is difference. This is a difference operator. With the help of difference operator, we are denoting delta f0 divided by h. So the interpolating polynomial is now your interpolating polynomial. The straight line is fx0 x minus x0 first difference operator divided by this h. This is the straight line equation of the straight line we have. So we need to recall, we need to remember this, that this is our interpolated polynomial of degree 1. fx0, this is a given one. X minus x0, everything is given. Delta f0 we will get from the table directly, divided by h. Our equation is ready of the straight line. Is that clear?
Yes, sir.
Yeah, only
Yes, sir.
only a different format. This is the equation of the line only, but we have written that equation of the line in this format, and we will generalize now this. So if we go to the quadratic case, when three data points are given, yeah, so x0 fx0 is given, x1 fx1 is given, x2 fx2 is given. Now three data points are given. So in this case, we will consider a polynomial of degree 2, b0 b1 x minus x0, b2 x minus x0, x minus x1. This is a quadratic polynomial, a general quadratic polynomial we have taken, but in this special order, in this special format. And the same thing we will be doing, that x is equal to x1 point, x0 point, you will compute b0. So directly you got b0. So you will get all these coefficients without solving system of equations and so on. Now at x is equal to x1, this will be 0, and you can get b1 because b0 is known now. So you will get b1, and b1 also we will write in that, that is special for equidistant point, that b1 is nothing but delta f 0 over h. Okay, and then x is equal to x2, then b0 is known, b1 is known, so naturally you can get b2 easily. So our b2 will be, I'm just skipping those. So this is b2, right? So then you will take to the left hand side and so on, and
Fine, bro.
finally what is b2? b2 you will get here in this form, and you will see the numerator is coming as the double difference, the second difference there, delta 2 f0 over factorial 2 h square. So that is your b2. and the interpolating polynomial is coming like this one. Fx naught, x minus x naught, delta f naught over x, x minus x naught minus x1 delta 2f naught over factorial 2h square. So very easy to, yeah, please mute yourself. Someone has unmuted. So here the interpolating polynomial looks like this, the second degree polynomial. See, the first degree polynomial is sitting exactly like this, which we have discussed before. Fx naught, x minus x naught, delta f naught over h. Then you have added this term, that's all. For the third degree, again, we will have some more term here. Fourth degree will have one more term, will be added to this expression only, nothing else. Once this interpolating polynomial this formula is known, you will just put the values fx naught, delta f naught from the table, delta 2f naught from the table, and this is everything is known. Then you have quadratic polynomial directly without solving any system or any other equations, right? So in general, we are not going to now do for the 3 case and 4 case and so on. So suppose this n plus 1 nodal points are given, and then the formula will be like this: fx naught, x minus x naught, delta f naught, x minus x naught, the product, the second order, third order, and so the nth order. So I think very simple to remember, and we don't need to solve any system of equations. Whether you are talking about the 10th degree polynomial or 20 degree polynomial, doesn't matter. That you can directly just write down that table. In fact, you can prepare easily that those are just the differences, nothing more, and put those from the table. So as I said, in the Newton's forward difference formula, this delta f naught, delta 2f naught, delta 3f naught, and so delta nf naught, and those values were exactly those top values where you have fx naught, and that was delta fx, and then delta f2 and so on. So those values will be used here, the top values in your table. That's fine. That's clear. There's another form.
Yes, sir.
Another form is just a shift. You can make it that x minus x naught over h, you can say that is your u. So basically x you are defining by a new variable u, so that some simple looking formula will come up. So x is x naught plus hu, and then you have this absolutely the same thing, nothing else. We don't need in numerical computation all those shifts and all. Just for some reasons I'm just putting this, because deriving the other formula will be very easy for me now to go for the backward once I have this form. So here this just a simple substitution, and my new formula in terms of u is given by this expression here. I think we'll take a quick break here, and then we will go with the Newton's backward and then some examples. Yeah. So I think you have no problem up to this point, right? We have derived this first order very simple way, and then the second order also, and then we have generalized this. Yeah, that's all. This is called Newton's forward difference formula. Newton's forward difference formula. What is the advantages? You know. Yeah, we need to only prepare the table, put those values there, and then the rest everything is known to us. Correct? So that's the beauty. So we'll start from this point itself.